Hello there, Mr. Sutton here, bringing you the BC Calculus 8-2 Part 1 homework solutions on arc length. For this calculator problem, I need to set up and solve an integral for the length of this curve from negative pi over 3 to pi over 3, and this is x equals something in terms of y. So let me first take my derivative here. I know I'm going to need this for the arc length formula. dx over dy, that's the derivative of secant of y. That's just going to be secant y tan of y. And now I'm going to plug this into my arc length formula. So I'm going to have the integral from negative pi over 3 to pi over 3 of, and now we're going to have the square root of 1 plus dx over dy squared dy. I've already defined what dx over dy actually is up here. So this formula will suffice. They know what I'm talking about now when I write dx over dy, because I said that's what it is up there. So I just have to plug this in the calculator. To enter this on the calculator, I'm actually going to put my dy over dx in y1, and I can write secant times tan as tangent over cosine, because secant's really 1 over cosine. So this is the fastest way to enter the secant function. Quitting out and going back to the main screen now, I did Math 9 to get my integral. We're going from negative pi over 3 to pi over 3. We have the square root of 1 plus, and I entered my dy over dx in y1, so y1 squared. That's part of why I did it. It's easier to square it this way. And then we're going to do everything in terms of x, just because our calculator doesn't really care what we put for that, as long as we're consistent. So enter, and that's going to give us 3.139 if I round that off. For this problem, I want the length of y equals ln of secant of x from 0 to b. And they're telling us that b is somewhere between 0 and pi over 2, which is important just so that we don't have any discontinuities on here. So let's use our arc length formula then for functions that are in terms of x. That's going to be this formula, integral a to b square root of 1 plus dy over dx squared dx. We're going to need dy over dx for this. That's the derivative of ln of secant of x. So this is going to require the chain rule. For the outer function, we have ln of something. That's going to be 1 over the something, 1 over secant of x in this case, times the derivative of the something, derivative of secant, which is secant of x tan of x. And I'm going to simplify that right now because this is a no calculator question. So this is going to be just tan of x. All right, plugging things in. I have the integral now from 0 to b, right there. Square root of 1 plus, we see that this is going to be tan squared of x dx. And we don't actually have to evaluate this because we don't know what b is. However, we do need to match one of the integrals here, and I don't see this exact expression. However, 1 plus tan squared, that should be tickling your memory a little bit, because there is a Pythagorean identity that says 1 over tan squared of an angle equals secant squared of that same angle. So the stuff inside the square root can actually be converted to secant squared of x, and the square root of secant squared of x is just secant of x. So the integral from 0 to b of secant of x dx is really what we're looking for, and that's answer choice A. For this problem, we want to know the length of the curve defined by these parametric equations from 0 to 1, or at least something equivalent to that. Since I'm going parametric here, I'm going to use my parametric length formula with the square root of dx over dt squared and dy over dt squared. So dx over dt, oh, by the way, this is going from 0 to 1, so that's our limits of integration. Dx over dt, that's the derivative of t squared over 2. Using our power rule, the 2's cancel. We just have t, but that's being squared inside there now. And we also need dy over dt. That's the derivative of t cubed over 3. 3 times 1 over 3 is going to cancel. We still have t squared, and that is being squared inside here. Cleaning this up a little bit to match an answer choice. This is a t squared plus a t to the 4th. And that's going to give us choice D. For this mess of a question, we want the length of the path of the parametric equations x equals cosine cubed of t and y equals sine cubed of t between 0 and pi over 2. So since we're going parametric, we're going to use our arc length formula for parametrics, which we're going to have the integral from a to b of square root of dx over dt squared plus dy over dt squared. So I have an integral from 0 to pi over 2. Let's put that in here. And now there's a whole bunch of stuff happening inside here. Looking at the answer choices, this is going to require a little bit of simplifying. So let me do dx over dt first. That's going to require the chain rule. We're going to have we have an outer function of the third power here. This is something to the third power. So this is going to be 3 times the something, 3 times cosine squared of t, times the derivative of the something, derivative of cosine, which is negative sine of t. And that's all being squared now. We'll square it all in a minute. Moving over to dy over dt, this is going to be 3 sine squared of t times the derivative of sine, which is cosine of t. And again, that's all being squared there. Cleaning this up a little bit, over here we have 3 squared, which is 9. Cosine squared squared is cosine to the 4th. And negative sine is going to become sine squared of t. So there's our first term, simplified a little bit. For the next term, we're going to have 9 sine to the 4th cosine squared of t. And does that match any of the answer choices? Well, let's look for the one that has a big, long radical here. That would be, let's see, choice D. Yep, we have a 9 cosine 4th, sine squared, 9 sine to the 4th, cosine squared, just making sure everything matches, choice D. On this problem, we have a table with some values of f and its derivatives. Using a left Riemann sum with 3 subintervals, we're going to figure out an approximation of the length of f on the interval from 1 to 7. So if we're talking arc length, we've got a function that's in terms of x. So in general, we need integral from a to b of square root of 1 plus dy over dx squared dx. So this means we have the integral from 1 to 7. And in this case, we're going to be doing the square root of 1 plus f prime of x squared. Great. But now we don't know the exact f prime function. We just have a few values of it. So we have to use a Riemann sum in order to approximate this. So let's see here. I have subinterval lengths of 2. We're going from 1 to 3, 3 to 5, 5 to 7. So that's always going to be a base of 2 for our rectangles. And for the heights, we're going to be using whatever we get when we plug in values of f prime on the left side of the rectangles. So my first rectangle I'm adding up here, I have a base of 2 times a height of square root of 1 plus this first f prime value of 2. And we're using the first value here because this is a left Riemann sum, so we're always going with the left of the 2 interval markers that we're using here. All right, my next rectangle, I have a base of 2 times a height of the square root of 1 plus 1, this left value here for f prime. And that's actually 1 squared, but it's just 1. And then we have a base of 2 times, let's see, square root of 1 plus 0 squared. But we have to simplify this to actually match an answer choice. So this first one is 2 radical 5. And notice I put approximately equals here because this is a rectangle approximation, not the true value. So this stuff now equals 2 radical 5. This is 2 radical 2, 2 radical 1, which is just 2. So that's going to be answer choice D. On this problem, we've got R, the shaded region between this exponential function and this line down here, y equals negative 2x, and this vertical line. We want to start by finding the area of R. So for area, I need an integral. Let's see, since these are in terms of x, I can just basically go top minus bottom from left to right. So then my limits of integration, I'm going to be going from 0 to 1. And top minus bottom, that's going to be x e to the x squared minus negative 2x, so plus 2x, and then we'll have a dx in there. Now, the trouble is that this is a no calculator question, so I have to do this by hand. So this is a little bit tricky to do by hand. The key on this one to starting it off is I can factor out an x. If I do that, let's see what happens. So I have x parentheses e to the x squared plus 2. Now here's the reason this is a really good situation. I now have a situation where I'm multiplying two things together, and one of those things, x, is actually going to be at least part of the derivative of the stuff inside here, of e to the x squared. So I can use a little substitution to make this happen. I'm going to let my u value on this one equal x squared, because the derivative of x squared is 2x, and that x will cancel out with this x over here. So let's say u is x squared. Du then is 2x dx. And then we have to divide by 2x to get dx by itself. So that's du over 2x that I can replace dx with. I also have to get my u values. If u is 0, or actually if x is 0, then x squared u is also going to be 0. If x is 1, then u is 1 squared, which also happens to be 1, so that actually works out nicely. Plugging things back in, I have the integral from u equals 0 to u equals 1. Happens to be the same numbers. We still have an x here. We have an e to the u plus 2. And then dx we're replacing with du over 2x. So advanced integration helping us out on a free response here. The x's are going to cancel, so I've really got 1/2 e to the u plus 2 that I can pull out there. And now let me go ahead and take this antiderivative. So going from left to right, antiderivative of e to the u is also e to the u. And we have a 1/2 hanging out outside here. So we have an e to the u. Antiderivative of 2 with respect to u is going to be 2u. And we're evaluating all this from 0 to 1. So I have 1/2 times all of this with 1 plugged in. And then in a big parentheses here, we're also subtracting all of this stuff with 0 plugged in. Now this is numerically equivalent to whatever the answer should be, so I could actually stop here now that I've got everything plugged in. If I want to keep going for some reason, I have 1/2, I have e, I have plus 2, and let's see, 2 times 0 is gone, but e to the 0 is 1, and we're subtracting, so minus 1. And if I still wanted to keep going for whatever reason, this is 1/2 times e plus 1, so we can write e plus 1 over 2.
For this part of the problem, they want us to write but not evaluate an integral expression with the volume for the solid generated by rotating this thing around the horizontal line y equals -2. So I took a moment to actually draw that line just so I have a good visual of what's going on here. Y equals -2 is down here where these two lines intersect. So it's this line right here. If we're revolving this solid, or this region actually, around this line, that means we're going to have a gap between our bounded area and the axis of revolution, which means we're going to have to use washers. Before I even set anything up, though, in order to make this a little bit easier, I'm actually going to give these two functions names. I'm going to call this first one, this x e to the x squared one, f of x, just so I don't have to keep writing it every single time I want to use it. And then this other one, the line -2x, I'll call that g of x. So using washers on this one, I have my cross-section area is a donut, so I'm going to have pi times big R squared minus little r squared. Part of why I renamed these functions, big R is this exponential function right here. That's further away from the axis of revolution. But I can't just call it big R because there is a big R already. It's the name of the bounded area. So I'm going to call this f of x right here. So my big radius, it's actually going to be the distance between this exponential function, which I've called f, and the line -2. So f of x minus -2, or f of x plus 2, and I'm going to be squaring that. So that's going to be my big R squared for this one. We have that pi out there still. And now for my little r squared, well, I've got the distance between the g function here and this line. So g of x plus 2 or minus -2, squaring that and adding it to what I already have in here. And this big crazy mess is my a of x function. So in order to get the volume, all I have to do is integrate this area function over the correct integral. So the interval I'm going to use is from 0 to 1. So my volume is going to be the integral from 0 to 1 of, I'm just going to write a of x dx. For this last problem part, they want us to write but not evaluate an expression with an integral for the perimeter of this R region. So I'm going to start, because there's a lot of different things going on here, I'm going to start by labeling each side of this. So I've got A, I'll call this one over here B, this will be C up here, and I'll just find them individually, and then when I'm done, I can just write perimeter equals A plus B plus C. Okay, so let's figure out A. A is the distance along this line here. Quickest way to find that is to think of this as the hypotenuse of a right triangle and use the Pythagorean theorem. So I'm going to have a square root of, I basically need a squared plus b squared. So I have the distance from here to here. I'm going to square that, so that's going to be 1 squared. And I have the distance of this height here down from here to the x-axis down to this intersection. Now how low does this go? Well, we did on an earlier problem the line y equals -2, and we saw that it went right through here. But if you weren't really sure, if you plug in 1 for x to this line right here, you get -2 back. So this is a distance of 2 then that I can go ahead and square. And let's see here. I guess if I really wanted to, I could simplify this to square root of 5, but I don't really have to, so I'm just going to leave it the way it is. Moving on to b now. B is going to be the distance between this y value up here and the y value down here. We know this y value down here is -2. We just talked about that. But up here, what's the y value? Well, that's going to be what I get when I plug 1 into the f function, what I've called the f function right here. So that's going to be f of 1 minus -2, which is really g of 1 here. So I guess if you wanted to write that out, 1 plugged into this just gives me, let's see, 1 times e to the 1 squared, that's just e. And we're adding 2 if we're subtracting -2 here. So e plus 2 if you want to simplify that. And then next, I need to figure out this c distance. So this is going to require my arc length formula, which means I'm going to need the derivative of the f function here. Let me go ahead and write that out now. F prime. To get this, I'm going to need the product rule. We have 2 functions being multiplied, and I'll use my box and ribbon here to organize this. So I have x as my first factor, and then e to the x squared is the other one. Now the derivatives of these, x is going to become a 1, and e to the x squared, that's going to require the chain rule. So I have the derivative of the outer function, e to the something, which is just e to the same something, e to the x squared, times the derivative of the something, derivative of x squared. So we're multiplying by 2x, and then using the ribbon to put all that back together, I've got 1 times e to the x squared, so that's e to the x squared, that's the u prime v, plus, if I just combine like terms here, this is going to be 2x squared e to the x squared. So all of this is my f prime. Now, if I want the actual arc length, since we're doing this in terms of x, I'm going to need an integral from a to b of, let's see, this will be square root of 1 plus dy over dx squared dx. So this is going to be an integral from 0 to 1. And inside I've got 1 plus the square root, or actually just the square root of 1 plus f prime squared. All of that with the dx out there. So I've labeled what f prime is. It's this craziness right here. I have an integral with this f prime being squared and everything else being followed. So I've got the c that represents this arc length now. All right, now for perimeter as promised, we're just going to do a plus b plus c. And this satisfies what they wanted. They wanted an expression with at least one integral expression. Check. So yeah, we're done.